All right. I hope you can see my slides. Okay. So today we will go on and finish chapter 3. Let's see how much we can cover in chapter 3, and we'll try to do. Okay. So chapter 3 is talking about the processes inside an operating system. So how is the process being done? How is the process being created? And what are the components inside the process? And what are the states inside a particular process? Okay. So it is hoped that by the end of chapter 3, or halfway through chapter 3, you will be able to understand what is a process, what is the program, and what are the types of state that a process goes through before it's completed. Okay, so a process goes through several states, several types of condition, from zero to a certain output for it to finish running or finish doing its job. So you have several states and several conditions before the process can finish or before the process can start. So we are going to cover the process concept and the schedules behind the process, and what are the specific operations in the process, and how does the process communicate with another process. Okay, because some of the processes are linked to one another. Okay, so the operating system will have a mechanism for the process to connect to another process, or within a process there are several processes, several small processes within one process. Okay, so that also will be covered in today's lecture. Okay, so the objective of chapter 3 is to introduce the notion of what is a process, a program in execution, which is the basis for all computation, describe features of process, okay, explore the inter-process communication, and describing the client-server system itself. Okay, so first of all, we need to understand certain terms. What is the process concept itself? Okay, so there are several terms that the books use or you can find. Some say job, some say process, but as you look in point number 2, the word job and process are almost the same. Okay, so in an operating system, okay, you have several types of job or several types of process. So in a batch system, you call it as jobs, and in time sharing system, we call it as user programs, or what we say as tasks. Okay, so there are certain parts of the process that you need to know, and we will cover that along this chapter. Okay, point number 3, a process is a program in execution. This is very important. A process execution must progress in a sequential fashion. So what does that mean? A program, what is a program? A program is what you say as, for example, Microsoft Word, Microsoft Excel. This is a program. So once the user clicks on it, it automatically changes from a program to a process. What happens behind it? Okay, it starts opening, it opens the first screen, so that is a process. Okay, so until when it opens the first screen, from the time the user double clicks on it until the first screen appears, that is a process. That is process number 1. Process number 2 happens once the user starts using Microsoft Word, starts saving, starts printing, so that is process number 2. And once the process is terminated, the user shuts down that particular program, so that is what we say as process termination. Okay, process termination or program termination is the same. Okay, all right. So in each in each process, there are certain codes, certain counters, certain files, certain memory location, and information that is needed for the process to run. Okay, in order for the process to run, in order for the process to be executed, it needs to have certain codes, certain memory location, certain files for it to run, okay, for it to process. So we will cover that along this chapter. Okay, so again, program is passive. A program does not do anything. It's passive. That's why it's a process is, on the other hand, an active. Program becomes process when executable file loaded into memory. A program is just a program. So once the user double clicks on it, it becomes a process and it's loaded inside the memory. So why do they say executable file? Executable file is that file, we have the extension exe. So that's an executable file. So the user clicks on that particular file, it becomes a process, and it's loaded inside the memory. Execution of a program starts via GUI mouse clicks, command line entry of its name. So the execution of the particular program starts when the user double clicks on a particular program. Or you can use the command line interface whereby the user types in a special command. Okay, so one program can have many processes. One program can have many processes. So it can have several processes in one program. Okay, so along the way, this chapter we will understand how is that possible. One program, many processes. Yes, it is possible. Example, when you open Microsoft Word, okay, so process number one or the main process is to open the Microsoft Word, but there's also several other processes running inside it. Example, it will check, Microsoft Word will check if the last document that you did in Microsoft Word, was it saved? Okay, if it's not saved, it will come up with a message. Okay, or it will check if, okay, or if there is anything printing. Microsoft Word, they can check. If you want to open up file, they want to check. Okay, and then these are several processes which happen inside the same particular program. So can we say one program, one process? No. There can be an instance whereby you have one program and many processes. Okay, so you can assume that multiple users executing the same program. Okay, that's how you mean. You have multiple using, but all doing the same program. Okay, once a process is inside a memory, okay, once a process is inside memory, this the information about the process will be transferred, will be kept inside the memory. So there are certain informations which are kept about the particular process. So these are the types of information which is kept inside the memory. So you have the data, you have the text, you have some heap data, and you have the stack. So these are all information about the particular process inside the memory. Okay, so this information is kept inside the RAM. Why? Because that particular process is running at the moment. Okay, so these are certain informations. So if you have two programs, two processes, how does that do? Yes, if you have two processes or three processes or four processes, the same information will be kept inside the memory. So here we have several states of a process. So you have the new state, and then and then you have the running state, you have the waiting state, you have the ready state, and you have the terminated state. Okay, so the new state is whereby when the user double clicks on a particular program. So that is when the process is being created. Okay, the new state, Okay, the new state is whereby the user double clicks on a particular program and the process is being created. So where is this new state? The new state is inside your hard disk. Why do I say that? Because the program is inside your hard disk. It's always inside your hard disk. It's nowhere else. So once the user clicks on it, it becomes a process, and now that particular process is being brought or is being admitted inside the ready state. Where is the ready state? The ready state is inside the RAM. Okay, inside the RAM. Okay, next, it wants to run. That means now, tadi, the user double clicks on it. So it becomes from a program, it becomes a process. So now that process is being admitted inside the memory. So next, it wants to run. It wants to execute. It wants to open up. So it goes into the running state. The running state, where is it? Is inside the CPU. Okay, it's inside the CPU. Next, okay, it can happen whereby the process is waiting for something to happen. Probably it's waiting for an input by the user. Because user tak lagi kat keyboard. So it's waiting for some event to occur. So in this particular state, the process moves from the CPU and goes back inside the waiting state. And where is this waiting state? The waiting state is inside the memory. Okay, it's inside the memory. Once the input comes in, for example, once the input completion or once the process gets that particular input, the process goes back into ready, which is also inside the memory, and automatically goes inside the running state, which is inside the CPU. That's why when you see ready is the process waiting to be assigned to a processor. So it's always waiting inside the memory. But it does not wait long, because this cycle, running ready, happens very, very fast. Okay, so next, once the process is terminated, it's finished. So now it just executes and go back into the hard disk. Right. So I think that's quite simple. Next, you have also something which is called the scheduler dispatch. The scheduler dispatch takes the process from ready into running. So what does that mean? Okay, what does that mean? And what does the interrupt mean? Okay, what does it interrupt mean from running to ready? Okay, sometimes when we are doing our program or our Microsoft Word, for example, you get an interrupt. So what is the interrupt? Probably you printed something and the printer has run out of paper. So now the printer signals back to the personal computer and it gives you an interrupt on that particular process. So when the process gets an interrupt, it automatically goes back to the ready state, which is inside the memory. So it's from the running, now it goes back inside the ready state, which is inside the memory. And it waits for the printer or whatever to complete its process. Once it's completed its process, there will be a scheduler to choose the process back to running. Why do we say choose? Because there might be several other processes inside the memory. So a scheduler needs to keep track which process was first, which process needs to go out, and so on and so forth. Okay, understand this? So inside a process, we have something which is called a process control block. The process control block is a unique feature is given to each of the processes. So each process has a unique process control block which keeps several information about that particular process. One is the process state. Is it either running, or is it waiting, or is it done? Okay, so that is a state. So that is why these circles here are known as the state. What state is the process? Is it in the waiting state? Is it in the running state? Is it terminated, or is it ready? Okay. Next, we also have program counter. Program counter is the location of the instruction to next execute, because now the process is running. So the process needs to know what is the next instruction to execute. What does that mean? Actually, in order for you to eat, okay, let's assume eating is a process. Okay, eating is a process. So you have several states inside eating. Either you're waiting to be served, either you're already eating, or either you're taking the plate. Okay, that's your state. One, you might take the plate. One, you might cedok nasi. One, you might start eating. One of you might be waiting for the queue to move. So that's your state. Okay, let's assume that you have taken your plate. So that's the state. So now program counter will keep track of what is the next state after taking the plate. What is that? So you have to take the rice, and the next program counter will be, okay, after taking the rice, what is that? So that is what we say is a program counter. You will keep the next instructions after that. Okay. Next, you also need to, the process needs to also keep a CPU register, because the process is being run inside the CPU, so it needs to have a register. Okay. And then it also needs to keep track of the CPU scheduling information, because sometimes while the process is being run inside the CPU also gets other requests to run the process. And some of these requests are important. For example, let's say they are coming from the printer, maybe there's a blue screen coming in, information is coming in, so these are priority, so it must run this first. Next, you also have memory management information. So which location of the memory is allocated to a particular process. So I repeat, which memory location is given to that particular process. Okay, so you have, as you know, the memory is very big. So which particular location is given to the particular process. Next, the information inside the process control block is accounting information. How fast, how slow, when did it start, what is the CPU usage, and these are information about the process control block. And finally, which I/O devices, output devices, is allocated to the process control block. Or what it means is which I/O devices can be used by the process. Okay, can be used, I mean, boleh digunakan oleh proses. All right. So next, we also learn how to about if there is an interrupt on the process. Okay, so let's say process 0 is running, is executing. Suddenly, it gets an interrupt. So when it gets an interrupt, it will save whatever it's doing inside the PCB and save the state. So what is the state? Ready, waiting, ready, waiting, running. Okay, these are the states. So you will keep the state inside the PCB. Okay, you will not keep it the state inside the PCB, but it will, what do you say? It will save the current process, and it will put it inside the memory. Okay, so once it sits inside the memory, so process 1, it was idle now. So now process 1, sorry, okay, now the interrupt begins to process. Next, once the interrupt is done, it goes back and loads balik process PCB2, PCB0. So it's basically when the process 1 is running, when an interrupt comes in, it will stop, save itself inside the memory, and process number 1 or process number, the next process will start processing until it finishes. Okay, next we go into the term called thread. What is thread? Thread is a process, okay, is a separate flow of execution. This means that your program will have two things happening at once. Process that has a single thread of execution. Okay, so what is a thread itself? A thread is basically a process inside a process. Okay, a process inside a process. So the thread is the small process, you can say. Okay, the small process running inside the particular process, and it can have a separate execution. Okay, a separate execution. For example, let's say I'm running this Microsoft, what you see here now, or PowerPoint on my screen. So this is the main process. At the same time, I can also update, or I can also view, I can update, I can also do, or I can also do several other processes with the same Microsoft PowerPoint. Probably if I open two slides, I can print on the other slide, while at the same time I can read this slide. Okay, so a thread means from the same process you can break into two or more, and each broken process is what we say is a thread. Okay, so multiple locations can execute at once, multiple threads or control threads. Okay, so meaning one process has many sub-processes, and those sub-processes are known as a thread. Okay, so but each thread is kept, the information is kept by the operating system under the process control block under program counters. Okay, all right. So to maximize CPU usage, okay, so maximize CPU, because we want to maximize CPU usage. Why? Because we want to make the best out of the best from the from the CPU. So maybe there are some process which involves a lot of calculation. Maybe there's some process which involves a lot of printing. Maybe there's some process which does not do anything. It only waits for input output to come in. So the CPU must actually schedule itself so that at any one time it's doing something. It maybe, let's say it's doing a lot of input output. So, or maybe it's not doing any input output, it's doing something else. It's waiting for another process. Or maybe it's not waiting, it's doing something else. So there must be some process scheduling so that it's not only doing one thing at one time, it's doing multiple things at one particular time. So we have a scheduler to select the processes and determine which program is going to run in the CPU. Okay, so there is a queue. To choose process from the ready queue and device queue. So the device queue is something new. So it will choose which process from these two queues to be put inside the CPU or inside the processor. Okay, so here you have your ready queue, which was the same thing as this now, the ready set, and from the ready it goes into the CPU. However, the process might request an input output, or might have a time slice, meaning after a certain time it expires, or might fork a child. Fork means it breaks into the next process, or it opens up another thread, okay, or might wait for an interrupt. So these are types of processes. So these, for example, input output request. Let's say maybe this process requires an input output. It's waiting for let's say an input. When you scan your betul dekat kedai tu yang barcode reader tu, so it's waiting for something to happen baru dia boleh jadi. So that process goes inside the queue and wait. Or maybe there's a time slice. Contohnya when you're doing Maybank to you, the time slice. So after 1 minute, if there's no input, automatically system expire. Or maybe the process executes a fork. That means it breaks. It goes into separate location. So it goes into a thread, and the thread can keep running, can keep executing. Okay, so there are certain ways. or is waiting for something to happen, is waiting for interrupt, it's waiting for an input from the user. Okay, so these are types of queuing diagrams which are available, and how does the CPU handle all of this. Okay, so in order for the dispatch or the scheduler to choose what particular program, so it must choose the best process, because it cannot choose something which is all the time CPU bound. That means all the time doing computational, all the time the CPU is active. Or you cannot do something which is waiting for input output. Okay, that means it's doing something and it's waiting. Let's say one process is waiting for an input, so the next process cannot do. All the processes which are waiting for input from the user cannot continue, because the first process, which is waiting for input from the user, has not completed. So we have two schedulers to choose from. One, the operating system will choose a short-term scheduler or the long-term scheduler. That means they will choose the processes from the ready queue to masuk dalam CPU. So mungkin dia orang akan pilih, okay, this time around ambil proses yang banyak buat kerja CPU. The next process ambil proses yang buat pasal input output. The next process ambil pasal CPU. The next process ambil pasal long-term scheduler. Okay, and keep on and on, going on and on. Okay, so the long-term scheduler controls the degree of multi-programming. So what does it mean by degree of multi-programming? Degree of multi-programming means you will choose the best process in so that it is maintained together. Okay, meaning sekejap dia akan bawa proses ini, sekejap dia akan bawa proses yang buat ini. So it maintains by itself. Okay. Alright, so long-term scheduler and short-term scheduler itu berbeza, two different places. From ready queue, that means from new to ready, that is a long-term scheduler. From ready to running, that is a short-term scheduler. Okay, short-term scheduler itu kenapa dia short? Sebab it has to bring very fast daripada memory to CPU, very fast. Tapi long-term tu dia long, so it's coming from outside, it's coming from the hard disk. So that one dia akan bawa daripada hard disk to the ready queue, which is the memory. Two types of process: input-output bound and a CPU bound. Input-output bound meaning proses tu all the time doing input and output. It's waiting ke dia keluarkan. That means it's either waiting for an input to happen baru dia start, or it's printing something and it's also input-output bound. It's doing something. Okay. There's also another process which is called the CPU bound process, spending more time doing computational. Contohnya macam program-program SPSS, mathematics. Okay, dia tengah buat CPU je, dia tengah buat computational je. Okay, and what we say is CPU bus. That means dia tengah buat all the CPU process. Okay, so my long-term scheduler ialah to get the process of a good mix, because we do not want the process to be always doing input output, always doing a CPU bound. Then what do we have? Like as a user, we have to wait or CPU tengah buat input output, or CPU tengah buat CPU. So it's going to be very difficult, and the process might just jam up. Okay. Next, we also have something which is called the medium-term scheduler. So what is a medium-term scheduler? Medium-term scheduler ialah if, okay, remove the process from the memory, store it on a disk, bring back from the continuum. This is what we say swapping. That means you tengah buat something, process, you swap it with another process. Okay, yang ni you pernah buat lah. Dia macam switching lah. You control alternate delete, you switch to a different process. Or you control tab, then you can see several processes too. Then you just choose what process, automatically the CPU will swap the process to whatever is appearing on your screen. Okay, all right. I think we can stop here. This you can read on your own. In the next class, we will start on context switch one. We will start on 3.3, which is the operation and on processes. Okay, so next class we will start on slide number 18, which is on operations and what do you say, operations and processes. Okay, all right. Any questions so far? Okay.
No, sir.
No?
No, sir.
No questions.
Okay, so I will leave you for now. Thank you so much for attending my class today. Do not forget to sign your attendance, and inshallah we will see you in the next class. Thank you so much. Assalamualaikum warahmatullahi wabarakatuh.